Yeah, I'm Colin from Dataloop. I'm here to talk to you about Dalmatiner DB, an open source time series database. I know you're all excited about hearing about another database, but you can't have too many. So I'm a bit bunged up. Okay, so in case you didn't know who we are, we're a SaaS-based monitoring solution designed for DevOps, people that are running services at scale. So we do the traditional stuff, whether your hosts are up or down, graphing your performance metrics, allow you to define alerts on those. Also, we give you a kind of an IDE in the browser so you can write your check scripts, test them on the boxes, and then deploy them to start monitoring your hosts. We also just recently added some more enterprise stuff so that you have a kind of account model to your organization so that you can add, remove users and specify which accounts they can access, which allows kind of DevOps to define their infrastructure, their monitoring infrastructure, and then allocate it to the kind of microservices teams that are looking after that. Okay, so in terms of time series, before we started using Dalmatiner, we were kind of we had this kind of approach. So we had a big fat pipe of metrics that were coming in via RabbitMQ. We basically kind of processed that and then dumped them onto Redis. Redis kind of sat there, built up some buffers, and then we had a separate worker that would run and build roll-ups based on that data and push them into Riak. So we'd have different resolutions of the data stored into Riak, which improved for the read queries later on. So we would roll that up to 1 second, 1 minute, and 1 hour resolution of data. So if you wanted to query a month's worth of data, it was fairly quick to do that. And this kind of, as we started to sell the product, people started to use it, which became a problem, not for money-wise, but to maintain the system. And so we needed extra features on top of that people are asking for. So we wanted to have multi-dimensionals on the data. So here, for example, you've got disk usage. People want to tag those based on where they are or what they're running, and then be able to query based on that later. You can do that without the dimensions, but it's painful to query that. They also want wildcards so that you can specify a rough query, but then add some kind of wildcard parts in the as wildcards in the components of your path. So here you might want CPU star user, and to plot that either as an aggregation or as all of those time series as they come in. AAE is active anti-entropy. So Riak has this feature of kind of repairing itself as it's going along. That tends to run on a periodic cycle, so like once a week. And so once a week, the entire cluster will go mental and start to kind of fall over and alert. And it never went down, but it would cause side effects elsewhere. So that was a pain. Also, deleting data out of Riak is a fucking nightmare. So it is painfully slow to be able to delete data out of Riak. And so, we decided we needed to kind of look at other options. And we were building up a bigger team now so that we could start looking at these. So we looked at OpenTSDB, awesome tool based on HBase, but it was fairly slow for large range queries, and we felt that we could do better. Cassandra didn't really give us anything extra. We'd still need to build something on top of this kind of column store. Graphite, I'm sure people are familiar that it's kind of hard to scale with resiliency to this level. You need to have relays all over the place and kind of manually shard thing. InfluxDB was an interesting kind of proposition in the fact that it gave us all these cool features, but they tend to change the back-end engine every 2 weeks, and they're not backwards compatible either, so you need to pretty much throw everything away or do a manual migration to get the data through into the new version. The next one was React TS. So we kind of had we've kind of got a close relationship with the guys at Basho, and they gave us kind of early access to React TS just as we were kind of, just as we really had decided on Dalmatiner. We kind of gave it a quick overview, but it's more designed as a generic time series database that doesn't really work in our scenario. So to be able to get custom dimensions on the data, it would have meant exporting and re-importing the data based on the new kind of schema that had been defined for those dimensions, which was kind of, going to be too painful. So if we kind of step back a bit, a couple of months ago, well, 6 months ago, something like that, we decided to, so originally we'd built everything in Node.js. It was really quick, was painful at scaling in certain areas, but we could build stuff fairly quickly. And yeah, it was awesome for some certain things. So like as an API layer, it was great. The performance in terms of memory management was very painful. So you really get like a 1.5 gig memory allocation that you can use. Once you start hitting 1 gig though, it's garbage collecting like hell. So you end up just locking up the process. And as we've got time series coming in, we're caching quite a lot of data on the fly. And it just wasn't scaling. We ended up building like 16 nodes to process our, at the time, to process our time series data. And they were fairly chunky boxes. And yeah, it wasn't great. So we were looking at other things. So we started looking around. We looked at Java, Scala, Golang, even C, which would have taken us like 6 months to build the thing. And we'd been using RabbitMQ and we've been using Riak, and they're obviously all built on top of Erlang. And we were quite happy with how resilient and scalable they were. And so kind of did some investigation into Erlang. And just the way it's designed from a distributed systems perspective at the core, we liked that. It's designed to handle failure. It kind of encourages you to, instead of handling failures, just crash the process. It makes quite lightweight processes for you so that you can make concurrent applications fairly simply. It's a functional language. Yeah, it's been in development for 25 years, so there's lots of bug fixes that have gone into this thing. And so we spent about 6 weeks building the first Erlang process we were using, and we got kind of spectacular results based off of that. We ended up being able to halve the infrastructure we were using for that particular service we built. So yeah, to get back on track with time series, to kind of go over how there's some kind of key aspects to how time series data works. So the painful part is that you need to support high writes and high levels of reads at the same time. So you're trying to get the data in as quickly as possible, but then you also need to pull the stuff out pretty quickly as well. Another interesting aspect is the queries of the time series data tend to be range-based. So you're querying for usually it's like a time range of the data you're looking for, or a cross range, you know, maybe all of the CPU-based metrics for, all your CPU-based metrics. But a couple of the good things, though, is that the data is immutable. So you don't tend to update any time series data as it's coming through. You write it once and then you leave it, you move on to the next one. And another good one is it tends to have periodic consistency. So as your time series data is coming in, it tends to come in at a certain rate. So it's either every 1 second or every 30 seconds or every minute. It comes in that rate. Also, it doesn't vary too often, apart from kind of clock skews and stuff you might get. We tend to work around that in other ways. So yeah, we were kind of investigating these ideas, and for a couple of months we were playing around with the idea of using Riak Core to build a distributed system for storing time series data. We kind of like the idea of using Riak Core because of it helps you build the distributed systems, and it helps you build reliable ones as well. And yeah, we kind of like the way that scales, and it should enable us to scale linearly. And we kind of started investigating different things. But then luckily we stumbled across something that someone else had written called Dalmatiner DB. It took us a couple of months to be able to pronounce Dalmatiner DB, let alone spell it. So we ended up calling it internally DoggyDB. Yeah, open source time series database, written in Erlang, great. Uses Riak Core and ZFS. It's highly optimized for write throughput. I'll kind of go over some of the benchmarks a bit later, but you can get data in there really quickly. We did some initial investigation of the code, obviously using Riak Core, ZFS, which we kind of liked, and it tended to be had a very elegant, simple design, and we were it was fairly. There was a lot there, but it was kind of manageable, something we could pick up and learn. And so, yeah, sorry, the URL's there. So if you want to play around with it, yeah, go on there, download it. It's a bit kind of rough around the edges because it's basically built by one guy, Heinz. He's a eccentric German guy. He's awesome. We went to meet him last week. He's basically built it to monitor his project FIFO, which is a cloud orchestration system for SmartOS. So if you're crazy enough to use SmartOS, then yeah, give that a try. Yeah, so he'd been building this thing for 3 years. We kind of stumbled across it. We thought, great, we'll give this a go. And so yeah, I thought I'd kind of give some information on what it is and how it works. So yeah, as I said, it's built on top of Erlang, on top of Riak Core, uses ZFS, and just recently we're in the process of adding some Postgres in there as well. You need a bit of Postgres. So for people that don't know, Riak is a distributed key value store. You basically specify a key, so here you got disk use and CPU idle, and you store a value against it. You've got integers, you can store JSON, XML, binary, whatever you want, pretty much. It has a concept of buckets, which are really kind of a namespace, a way of grouping keys. They use them for storing metadata against those as well. And so, for instance, here you might have a metrics bucket, and then you'd store all your metrics that are coming in as keys under that bucket, or yeah, users, and you'd store all user profiles. So this is going to get fairly low level, but I need to kind of explain this so you can understand how it scales the way it does and how it performs well. So Riak works on the Dynamo paper principle, consistently hashes. So you have a key that will come in, and it knows how many nodes are in your cluster. So it will consistently hash those keys in such a way so that it can build up partitions of that data. So it will hash these particular values and specify a partition that they belong to. If you want replicas of your data, which you should do so that you don't lose it, it will put those keys onto multiple partitions of the ring, as it were. So multiple partition, your key will belong to multiple partitions. This is all managed by a thing called the vnode, which is a virtual node inside of Riak. It looks after one of these partitions. You have it's an individual Erlang process that runs and looks after this particular partition. And then Riak Core as a whole takes care of where that partition gets chucked on your cluster. So it'll get put somewhere, and it will take care of managing keys as they come in. So a write might come into your cluster. It will get sent off because it's consistently hashed. It knows which node to put it on, and it will send it to the correct vnode on the cluster. And so that vnode will take care of things like transfers. So if you scale up your cluster or scale down your cluster, it knows that it needs to grab keys from somewhere or pass them off to somewhere. And so yeah, if you scale down, it will start handing off the keys onto another partition, so another vnode in your cluster. Also great for failover and redundancy, that if a node is inaccessible for some reason, you've got a network partition, the processor's crashed, it's just not running, can't access it at all. If it comes in and it can't access one of the parent vnodes for that particular key, it will pass it off to another one. And then when the primary one comes back up again, it will hand those back off to the correct owner for that particular key. And another great thing is it's masterless, so you don't need to have a particular node online. It handles network partitions great because it will accept all reads and all writes. They might not necessarily have the most up-to-date version of the data, but it will just work. It'll always be available, unless the whole cluster goes down, obviously. So what's Riak Core? So Riak Core is a library that is used as the kind of basis, the core, as the name says, of Riak. It's really built it's been abstracted as a distributed systems framework, and it provides you a set of services so you can build your distributed systems based on this. So you've got, it's used for managing the cluster, tells you if the nodes are up and down in that cluster. It handles the partitioning and where keys should be distributed to. And it also gives you information about the state of your cluster, how well it's performing, and which nodes are working properly. And I guess one of the coolest parts is it gives you these tools. So it gives you these tools for managing your cluster. So if you want to add a node into your cluster, it gives you the command line stuff for adding nodes in there, taking nodes out, reporting state about your cluster, all for free pretty much. Obviously, when you do your implementation, you have to adhere to the particular interfaces, but you get all that stuff out of the box, so you don't have to build it all for yourself. So in terms of time series, the time series comes into the Dalmatiner cluster, and then it gets allocated a vnode that particular metric path should go to. And one of the key aspects to getting the speed it does is it, as a metric path comes in, so your CPU idle or whatever, it will get, that particular value will get chucked into a buffer. That buffer is based on a number of points. So, sorry. So, based on the buckets you're using, you'll specify what resolution you want to store that data at. So, for instance, if you wanted to store a 1 second resolution of the data, and you want to keep 2 minutes in memory buffered, then you'd specify you want 120 points there. There's a constant kind of battle between I/O and memory usage. Obviously, the more buffer space you keep, the more memory it's going to take up, and it reduces the amount of I/O you're using. And so a metric will come in, and it will allocate it a place in that buffer based on the time it come in. So you'll have a place in the buffer for every second if you're using 1 second resolution for that point. So here on the top one, so a 1.2 come in for a particular metric, then the next second nothing come in, the second after 2.4 come in. So allocate that space anyway. And so it's really quick for it to do the lookups because it knows whereabouts to find the data. And it's also using 8 bytes of storage per point. Okay, so once you've filled that buffer, once the buffer's timed out and it needs to flush that, it flushes it straight to flat files on disk as is. And you could change this obviously, but by default it comes in 1 week. So you'll have a file per vnode, so per collection of keys per week. So you'll have the data come in, it will get flushed through that buffer, and then it will get chucked in a point in this file. And that file, it allocates a week at a time. So if you have no data in there, or like 1 point, you'll still get a week's worth of points allocated. They'll just be filled up with null values. And then so it also adds to an index for that. So your first metric will come in, it'll dump it into the index, then it will chuck the points for that buffer in, and then the next metric get chucked in weeks further on in that file. And then when that metric comes around for the next flush, it just adds it onto the end there. So if you only have if you set up for 1 second resolution, but you only fire in a point every 30 seconds, you'll have a point and then 30 gaps, then another point and then 30 gaps. But it allows you to have really fast lookups. So when a request comes in to pull a particular key, it can look in that file, which is often cached as well. Look in that file, it's just ordered based on where the position they are in that file. It knows where in the file it is and pulls it out straight away. So it's amazingly quick to look up data. Obviously, storing all these null points is a massive waste of space. And this is one of the cool aspects to having ZFS there. So ZFS will compress all of those null points, and it will compress that data as you're storing it. So, and it has the cool copy on write feature, so you never end up corrupting your writes as they come through. Having all that means that we can store a point on average using 2 bits per point based on our compression ratio we're getting through at the moment. It's roughly 2.1, but 2 bits sounds better. So yeah, that's kind of it really. So this is the back-end component for the Dalmatiner. There's 2 parts. There's a back-end and the front-end. Back-end is the store. It's really the database for storing the files, for storing your time series. The other part is the front-end. So the back-end is the ring of data. The front-end will sit there and listen for queries. So you can specify kind of a SQL-style query. Here we're doing a lookup for, specify the host you want it from, which is really the bucket. The metric you want, so here we want base.cpu, which happens to be a metric. Sorry, this is all the metric, but my host.base.cpu, and then the bucket is just just the way we use buckets. It's a kind of an optimization we used inside there, because obviously when you have, based on how you structure your buckets, depends on how many files you have open. So if you have one file open and you end up having a lot of vnodes, then you end up blowing the number of files you can have open. Okay, so this will pull out the data and then do a 30-second average on all that data that it's pulling out for the last 30 minutes of data that it's got. So it's a fairly simple query mechanism, but it's also quite powerful. So we can build these different aggregations on top of the data. And all it does, it will really gets that query in, parses that, builds up the tree, and will then know which keys to pull out of the back end. It will then pull all those keys out, process any stuff that's not needed, do any aggregation functions that are there, and then returns the results back to the user. So there's quite a lot in there, but it does a fairly simple job. Well, say simple. Okay, so one of the other things is people start using Docker, and you don't have a host really. Nothing. It's not associated with anything. It's just a metric. So to be able to handle this, we need to have multi-dimensions in our data. So yeah, these metrics really become orphans. They don't belong to anything. They are what they are. And so we started kind of, so we needed to add this feature. So the way this works is kind of still in progress. We've been working with Hemmings and a couple of our guys to build the multi-dimension stuff on there. We'll basically build an index up in Postgres. So it'll specify. So if you specify a metric path and a set of tags that you want associated with that path, that becomes a unique time series that gets stored and indexed in Postgres and then written to the Dalmatiner backend as it ordinarily would do. And then you can query that index if you're looking for, all metrics with a particular tag. It will then know which keys to look up, and it pulls the data out, and it goes through the same kind of function mechanism. Yeah, this is still in progress. A couple of the guys with Hemmings spent last Thursday and Friday prototyping this. They got a rough version working, and it's performing pretty well, but it needs to be kind of brought up to production standards before we can ship this. It also works with Grafana, which development team, our customers, developers quite like. So there's a custom Grafana plugin we have, and you can specify your data source as being Grafana, as being Dalmatiner, and then you can construct queries and build up your Grafana dashboards if you like using Grafana. Okay, so the cool bit. So Hemmings did these benchmarks, and then when we started using it, we tested them to make sure, because people have released benchmarks and they're all usually made up, or they're in a set kind of scenario which doesn't work for you. So we use Hagger, which, if you're not familiar, is a Graphite benchmarking tool. You can specify a number of paths, how often you want to throw data in, and it will just fire time series data in using the Graphite protocol. So Hemmings updated this to support the Dalmatiner. So this is another kind of rough thing about Dalmatiner. It has this crazy wire protocol, which makes sense from a performance perspective, but it's not easy to get integrated with Dalmatiner, because you need to basically reverse engineer the protocol to be able to get stuff in, unless you're using Erlang. So yeah, he did, and we tested this Hagger against this cluster setup, firing data in. Initially we tested at the bottom on the single node, getting 1.5 to 1 million. These are unique time series as well. They're not just one time series with 1 million points per second coming in. The cardinality of the data is vital to how quickly you can process that data. So these are unique time series as well. So everyone is different. So you can't do any aggregation as part of pre-processing to get the data in there quicker. And he had some. It's a fairly beefy box, but yeah, he had 5 of those and was getting 9 million metrics per second, which compared to anything else we've tested, kind of blows the pants off of those. This also, a pinch of salt with this had a replication factor of 1. So if you lost a node, you'd lose your data. but it scaled linear with that. So if you did increase the replication factor, you'd have a degradation on this benchmark, but it would still be astronomical compared to anything else. Okay, so in terms of trade-offs, so there's no strict guarantees about your data. You could lose some of it, but for us, for time series, that's fine. If you use a couple of points here and there, you tend to work with time series in terms of trends. So you're looking at how data's behaving over a period of time. You can also configure your cluster, so you can set up the replication factor in terms of how many clusters how many vNodes it writes to, and how many you want to pull from when you're pulling the data out, to reduce the probability of losing any data or not being able to access that data. We kind of had to play around with the memory usage. So we have those in buffer caches, and when you've got lots of hosts sending in data and lots of metrics coming in, there's a lot of data to kind of cache. So we had to really play around with those caches, and also ZFS, Zeal needs a lot of that memory as well to perform pretty well. So you kind of had to tweak that a little bit. But yeah, it worked out all right. We also had to make some changes. Heinz had optimized the crap out of this to get data in as quickly as possible, but he was using it for his cloud monitoring, so it's pretty much a couple of people using it, whereas we have more than 2 customers, so we need to get better read performance on that. And so, yeah, we had to make some optimizations to be able to get the data out quicker. We also had to add support for floating point numbers. Previously, it was only supporting integers because the use case before that could kind of control what data was going in, so you could make sure you only pushed integers into it. So that was just a particular challenge because you can only use 56 bits for the actual numeric value for that data. I can get into that later, but it's quite boring. And yeah, as I said, the binary code protocol is awesome for speed, but you have to kind of look at the documentation and the code to reverse engineer how you get data in, how you communicate with Dalmatiner. And that's pretty much it. That's a whistle-stop tour of Dalmatiner. Yeah. Any questions at all?
Are you actually using ZFS on production?
Yes.
With Ubuntu?
Yes.
If the police come around, we'll take it off.
Yes, and proudly.
Okay.
So,
Is that 1404 OTS or?
it's the one true operating system of 1204. That's not my terminology, but we are looking to upgrade to 1604 once that's got packages available.
And we are hiring, so if any of you guys want a job, we've got an exclusive deal with Linux Recruit at the back of the room.
Especially if you know, especially if you know Erlang. That'd be awesome.
We'll pay you to work on free stuff. Anyway, well done, Colin.
So, right, time. Thank you.